Well, thank you very much, and thanks for having me. I haven't actually been to one of these events before, so I was really excited to come along, and it's a great turnout, which I'm very happy to see. As Karen mentioned, I come from Canada. I've traveled around a little bit. I was always really good at finding projects that happened to be somewhere else so I could sneak a little trip in somewhere. I must say, since being in Tasmania, I haven't really felt that urge as much because there's so much cool stuff to look at here. I've kind of just had my plate full of really neat things to look at from a geohazards point of view, which is a big part of what I do at MRT, and then also the glacial stuff that I'm going to talk about partially today. Specifically, the type of geologist I am, I look at the very, very recent geology, the kind of most recent portion of the geologic timescale. So it's very different than probably a lot of people in the room might have experienced with the types of geology that would be delving much farther back in time. Just the image up here on the right, this is the glacial map of Tasmania. Some of you may have known that there is a glacial map of Tasmania, but it was actually produced as a special publication of the Royal Society of Tasmania in 1965. It was headed by Edward Derbyshire, who just passed away a few months ago. But I kind of featured a few points in the talk because it's, I think, just a great example of how much information is out there, how great of a job some of the earlier geologists did in piecing all that story together without the really good resources we have today. We tweak it here and there, but they got a lot of the story put together 60 years ago. So this is a map of the part of the world I come from. Specifically, I'm from Vancouver, which 20,000 years ago was, right under the edge of the Cordilleran ice sheet here. Canada had two ice sheets, this big one, the Cordilleran in the mountains, and this much, much bigger one, the Laurentide ice sheet, basically covering the rest of the country. So probably about 95% of Canada was under up to 2.5 kilometers of ice. There are still glaciers left, not too many. A lot of the ones right now that we see in the news are such as Mount Waddington, Salmon Glacier, and this one here just outside the city of Vancouver. This is Consequent Glacier, which actually provides some of the drinking water for the city. And the thing that these three glaciers have in common is the reason they're in the news is they're melting really, really quickly. And the projection is that by the end of the century, only about 20% of glaciers in Canada, or in BC that are there now, will be left. So in a way, this is kind of what we would have seen in Tasmania, say, about 14,000 years ago when the last of the Tasmanian glaciers were melting. And so really a lot of the evidence that we're going to be talking about are some of these features down kind of outboard, there we go, outboard of the ice itself. It's all this mucky stuff right around the edges. Those are some of the things we're going to talk about today. So this gives you a bit of an idea, kind of not just where I'm coming from geographically, but where I'm coming from in terms of point of view. So basically, I did a lot of my education and subsequent teaching and consulting work and government work in a place where we're just full of glacial features. Now looking at Tasmania, this is a very iconic Tasmanian landscape. I'm sure probably everyone in the room will recognize this. So here we have Cradle Mountain. And perhaps when you look at this landscape, the first thing you notice is the really beautiful aspects of it. I notice those for sure, but I also notice all the little signatures of past glaciers. For example, all the sculpting of Cradle Mountain up here, the fact that we have ice smooth surfaces down here, ice basically would have poured down into the lake. The cliff right below this person is glacially sculpted. There's a little, sorry, wrong button. There's a little, what we call a tarn here, which is the little lake that sits in a cirque. That was a little spot carved up by a glacier. So basically, this whole thing would have been affected by ice in one form or another during the last glaciation, and in fact, glaciations before that. Oops, wrong direction. So other iconic parts of the state include the Overland Track, Lake St. Clair, Walls Jerusalem, Lake Rona, the Tyndall Range, the Henty Erratics just south of the Tyndall Range, Frenchman's Cap, and the Vale of Belvoir. And what a lot of these reserves and parkland areas have in common is that they were, Ben Lomond as well, they were sculpted in some way, at least partially by ice. Not necessarily glaciers, it might have been kind of ground ice in the form of permafrost, and we call that periglacial activity. That's the stuff just out kind of side the fringe of where the actual glaciers were. It's always good, I think, to think about why we're doing what we're doing. And part of what I do, I love it, I find it really interesting. But the reasons to be studying glaciers and their records are, in part, it's just part of our natural history. I think there's a real importance of understanding that. They're also responsible for shaping a large part of the landscape we have today, not just in Tasmania, but around kind of higher latitude and higher elevation parts of the world. They're really not just a thermometer of past climate, but also a range gauge, and that's not just past climate, but current climate. Basically, if you have cold, wet conditions, your glacier grows. If you have kind of warm, drier conditions, it shrinks. And there's also stuff in between where the glacier will do different things. So it gives us a little bit of a mechanism to measure what's happened, not just currently, but in the recent and also distant past. It's not just the local, it's looking at the regional differences. I always think of Tasmania's glacial record as being kind of the stepping stone between the Antarctic records and other climate records on the mainland. It's kind of that way to kind of link in between the two other regions. And the importance is not just understanding the past, it's understanding what the drivers and linkages are in terms of moisture and temperature and how things circulate. That helps us kind of predict a little bit better how climate might change, especially in the immediate future, the remainder of the century. One thing I do a fair bit of is try to compare different areas I've worked in to see how I can, kind of line up different parts of the glacial record from this site and this site, and kind of understand if that helps inform maybe how energy balances are working, say, through oceanic or atmospheric circulation. I also do a lot of geohazard stuff, and in a glacial or previously glaciated environment, it actually gives rise to all sorts of things that can go wrong if you're not expecting them in terms of landslides, foundation issues, drainage, those sorts of things. That's another reason that we want to understand glaciers in the past. And finally, I think just Tasmania's excellent records of past glacial effect really need conservation and dissemination. And that's some of the work that at MRT, different university groups elsewhere in state government, we're doing to try to document these sites and make sure they have the opportunity to be, say, flagged as geoheritage sites, and also just information about them be disseminated to the public. So just about the Quaternion times, or the geologic time scale. If you think of it as a long spiraling period of 4.5 billion years. In the Tasmanian context, about 3 million years ago, basically we were a submarine basin just off the edge of the Gondwana supercontinent. By about 170 million years ago, all those nice big dolerite sheets around the state that form a lot of our landscape were being injected into the host rocks. By about 60 million years ago, the Tamar Graben starts to open. Lots of volcanic activity around 30 million years ago. And then this orange bit here is the Quaternion, which is the part I focus on, so really the very, very last part of the geologic timescale. That's what I'm talking about today, really, in terms of the glaciers, the most recent glaciers in Tasmania's past. So really, this Quaternion period's about 1/20th of 1% of Earth's history, predominated by icehouse conditions, meaning it's mostly cold. But even though it's a short period of time, because it's the most recent, there was an opportunity for lots of surface modification to terrain around the world, especially in mountainous areas like Western Tasmania. But those impacts, they aren't everywhere. They might be kind of spotty, they might be thin. I think of it if you were really, really bad at icing a cake. The cake itself is everything else, and the quaternary stuff is the patchy, crappy icing job on top. Not all glaciers are equal. There's a whole range of types, and people have developed different names for them that we now apply, but there are two factors. There's really increasing distance from the ice source, and there's increasing size or volume of ice. So down here in the lower left, we have cirque glaciers. Those are really kind of cutesy ones. If you get a postcard from Switzerland, that's probably what you'll see, a nice little seat on the mountainside that the glacier's carved out for itself. Quite often when those grow enough and they start to coalesce, they'll fill in valleys and they become these valley glaciers. Just right here, if that valley glacier reaches down to the ocean, we'll call it a tidewater glacier. We didn't actually have tidewater glaciers in Tasmania because the ice didn't make it as far as to get to where the coast was at the time. If we get enough accumulation of ice, we get an ice cap. And the difference between those smaller glaciers and the ice cap is the ice cap has gotten so big that it doesn't care about topography anymore. It's not being controlled by valleys. It's just flowing out under its own weight in whichever direction that weight tells it to go. Sometimes they form these big Piedmont lobes, and then eventually, if you get a big enough ice cap, it becomes a continental scale glacier, an ice sheet. So what we have today in Antarctica and Greenland, and had previously also in North America, Fennoscandinavia, parts of Northern Asia. So that's the types of glaciers. Now, the question is, how do we make a glacier? Well, the simple answer is wet and cold equals ice. The caveat being, it's not just ice, but we have to have ice that persists long enough and builds up enough that it starts to flow under its own weight. So typically that happens at high elevation or high latitude. It doesn't have to be both. I've worked a lot in the central Andes in Bolivia, where it's a tropical latitude of 15 degrees south. You wouldn't normally think of glaciers, but because the altitude's 5, 6, 7 kilometers above sea level in the mountains, you do have some nice glacial examples. But the idea here is that you start with the snow, and the snow builds up over time, and it compacts under its own weight, and it becomes something called firn, which is just kind of think of like kind of almost large ice crystals, and they start to grow together in an actual compacted ice, and that compacted ice is what forms the glacier. So it's basically flowing as a plastic under its own weight from the accumulation zone down to the ablation zone. Basically, the accumulation zone is where we have the snowfall. The ablation zone is where we have loss of ice either through melt to water, or we have direct sublimation where it's going directly from a solid water, from ice, to a water vapor, a gas. Now, in terms of ice ages and glacial climates, you've probably heard the term ice age thrown around a fair bit, and it can be taken to mean a few different things. The way that geologists usually think of it is there have been about kind of 6 ice ages over the course of Earth's history, and really Earth's climate alternates broadly between these ice house conditions and hot house conditions. So just in terms of some of those records, if we look at it from kind of global events and also Tasmanian records, about 750 million years ago, we had something called snowball Earth, with basically global conditions were so cold for so long that glaciers were in huge parts of the globe. Big areas of ocean froze over. You had big slushy areas. Not the entire Earth was ice and snow, but a lot of it was. We do get those records in some parts of Tasmania, especially in the northwest and the southwest. They're quite old rocks. They're quite tectonized and ground up. They're probably beyond my capabilities to understand. I really go for the low-hanging fruit at the surface. The Permo-Carboniferous glaciations, about 300 million years ago, those are recorded in the base of the Parmener supergroup. There's a unit throughout that stack of geology throughout the state, which is a really common unit. It's the stuff that underlies the dolerite. There's a unit down at the base that records ice that was flowing off the margin of Gondwana into the marine basin that Tasmania was underlying at the time. We have at the Eocene-Oligocene transition, there's different places around the world where ice starts to be picked up, particularly in Antarctica. That's when the Antarctic record really starts picking up. We don't really have convincing evidence of that in Tasmania. The mid-Pliocene warm period, this is an area or a time I looked at a lot when I was in Bolivia. We don't have any records in Tasmania, but it is a really interesting time in the geologic record because that's the last time that atmospheric carbon dioxide concentrations were about the same level as what they're projecting for the end of the century. So this is kind of the hotbed that all the numerical modeling people for climate change use as their kind of example of what future climate might be like and what it might do. Starting about little under 1 million years ago, the glacial, interglacial cycles go from these kind of shorter 40,000 year periods to a longer 100,000 year period. And in a lot of places, such as in North America, that helped build larger ice sheets. But that's when we get our first kind of confirmed records that we know of so far in Tasmania. And then we have these MIS things. These are marine isotope stages. These are basically just cool periods that have been identified by looking at marine records. But there are two. There's MIS2 and MIS4 that together basically make our last glaciation. That was active from about 120,000 years ago to about 18,000 years ago. So these are the most clear records we have in Tasmania because they're the most recent. Something we have a lot in the northern hemisphere, but we don't have evidence for in the southern hemisphere is something called the Younger Dryas. And this was just a time of kind of short-lived cooling in the northern hemisphere. We had lots of glaciers suddenly surging forward and growing. We don't have record of that, interestingly, in Tasmania. But one thing to keep in mind is that over this period, basically Tasmania and Australia are separating away from Antarctica, and we're kind of on a northward drift. So even though there's temperatures changes in global climate, we're also drifting to a lower and lower latitude, closer and closer to the equator, which means that conditions potentially could be getting a little bit milder. But my point is that when a lot of our records here are, say, from 1 million years to present, during that million years, we haven't moved much geographically. It just hasn't been enough time to really have much of a latitudinal effect. Now, in terms of global cooling, so what's resulted in those alternations between long-term icehouse conditions and hothouse conditions, and what results in the fluctuations of cold and warm within each one? It's all about energy balance, and there's a bunch of different ways we can do that. I'll hit on a couple of the main ones quickly. Greenhouse gases, of course, I think we're probably all familiar with, basically things that develop in the atmosphere and help trap radiation that's reflected back off Earth's surface. So if you're renovating your house, this is kind of like putting double glazed windows where you just had single glaze before. You're keeping more of that radiation in, so it's going to help warm you up a little bit. So typically that's a warming effect. We can have fairly rapid changes due to very, very large-scale volcanic eruptions. The 1800s eruption of Krakatau in Indonesia actually resulted in a great, quite a temperature depression for a few years around the world. And that's basically because we've got stuff going up in the atmosphere that's reflecting away some of the radiation before it can get down to Earth's surface. You might also get a little bit of a similar kind of greenhouse effect just because you've increased things like carbon dioxide in the atmosphere. So you can usually get a cooling, sometimes later on a warming. So this would be kind of like pulling down the shades on your windows if you're thinking of it in a home context. And then there's the marine and atmospheric currents. So this is kind of how the main currents work in Earth today in the marine setting. So you see that we have cold, deep water circulating around. It hits places, it comes up to the surface as warm, shallow water. And basically this is a really effective way to move energy around the Earth, move cold water, move hot water. The configuration of the continents has been the same for the last few million years, but there are a few things that change a little bit. For example, and this can locally change, cooling some places, warming others, but things that can change is the Isthmus of Panama. When it formed roughly around 3 million years ago, that kind of cut off circulation that used to go east-west between the Pacific and Atlantic, and now it has to go elsewhere, kind of down south and out and around. During glaciations, when with the lockup of ice on land surfaces results in sea level dropping quite a bit, suddenly you cut off some of the abilities for water to make it through the different island passages in Indonesia and surrounding areas. And also, starting about 60 million years ago or more, when Antarctica and Australia start pulling apart, eventually you get to a point about, say, 30 million years ago where you create a wide enough channel that you get independent circulation down there too. So this is kind of like, well, you're not going to change the windows on the house, it's more that you just get a whole new heat and cooling circulation system. It maybe helps some rooms, maybe it makes other rooms warmer, some colder. But the one that we're really interested in for the recent glaciations is something called orbital cycles. These are named Milankovitch cycles after a fellow surprisingly not surprisingly named Milankovitch, who first proposed them. Basically, the idea is there are 3 different ways the Earth moves that affects how much solar radiation is getting to the surface. One of them is the shape of the orbit around the sun, so that's the eccentricity. So is the orbit more circular versus more oblate or kind of oval? The more oval it is, then you have times when Earth's much, much farther away at the far ends, much closer at the sides. So that results in changes the amount of radiation getting to Earth. There's the actual precession. You can think about it as the wobble. So as Earth kind of spins, that axis wobbles a little bit. And the other one is just the changes in the obliquity. That's the actual tilt of the Earth. These 3 all just work on different kind of periods, 100,000 years, 26,000 years, 41,000 years. But overall, when you sum up the total, they account for these temperature fluctuations that we know from the marine records. So we have the purple things to the right are kind of warm excursions. Blue to the left are cool excursions. The line down the middle is basically average global temperature as it is today. And so the idea is that during the purple periods, the top one there, that's the Holocene, that's the time we're in right now, which is basically a non-glacial time. And then the last glaciation is that peak out to the left. And then before that, we had the last interglacial, which is the next peak out to the right, number 5 there. Number 6 is the penultimate or previous glaciation, and we just go back that way. So you see, it's not just one glaciation. There are a lot of them, and throughout, say, the last million years, they're largely every 100,000 years thereabouts. So some of the terms we'll talk about today about the geologic time scale. The Holocene is the last 11,000 years. It's when we're in now. Before that, we had the late Pleistocene, which is basically the last glaciation. Before that, there's a middle Pleistocene, which has a whole bunch of glaciations. And before that, the early Pleistocene, which has many more glaciations, but notice that they aren't usually as severe in temperature change, but they're also not as wide, meaning they're not as long-lived. They're the 40,000-year cycles. I think our context is quite important here. There really isn't, there are lots of things that you can tell about glacial histories by looking at the marine record, and they're really helpful, and there are lots of people, lots of geologists who do that. But there are certain things that you can't get from the marine record. You really have to go to terrestrial exposures, and that's really the local specific context. If you look at the marine record, it's a bit averaged for a region, where if you want to know what was happening in Tasmania or South Island, New Zealand, you really kind of are better off to go to that spot and look actually in the field. Now, there are very few places in the southern hemisphere compared to the northern hemisphere where we have long records of glaciation. Part of that is the fact we just don't have as much landmass, other than Antarctica, sticking out into the temperate zones of the southern hemisphere. But we have a few, and some of these longer records, we have about almost 40 million years on the Antarctic Peninsula of glacial records. The Patagonian Andes, over 4.5 million years. And then as we get a little farther into Patagonia, it's about 1 million years. This is the area I'd worked on for my PhD in the tropical Bolivian Andes. So we've got a beautiful record there of 3.5 million years. So you kind of see just in a few spots that we have, a few million years here, maybe 1 million years there, including in New Zealand. The only other part of Australia that had ice during the last glaciation was the Snowy Mountains. That was only the last glaciation. There's no evidence of ice before that. And then finally, here we are in Tasmania. So Tasmania is kind of a bit longer than the New Zealand record, potentially. It's hard to say the New Zealand one's all chewed up from uplift. But I think the important things are that Tasmania is the only southern hemisphere site where we have a good glacial record in the absence of major mountain building. All these other glacial records in the temperate latitudes, so southern South America and New Zealand, they're happening in places where we have really rapid mountain building, which means, firstly, we lose some of our records due to erosion. It also means, though, that it's really hard to figure out, do we have changes in glaciation because the mountains are getting higher and therefore there are colder conditions at the top? Or is it due to actual kind of regional changes in temperature and precipitation? So the Tasmanian records offer an opportunity to kind of disentangle that a little bit. And yeah, again, it's the only part of Australia that had repeated glaciation in the geologically recent time. So basically, roughly where were those glaciations? I've got two maps here. This one on the right shows the maximum Pleistocene extent. So basically, where do we know there was ice at least some point in the last couple of million years? So you see it's actually quite a big blob, mostly on the, on the western and northern margin of the Central Plateau, and a lot of that ice kind of bled down into valleys draining to the north and to the west. We have little isolated bits, say, down around Mount Field and also in the southwest as well. So again, these are the maximum ice extents. This is as far as ice got. We don't know in all cases when exactly that was. If we talk about the last glacial maximum and look just at this one area here, so the last glacial maximum was kind of the end of the last glaciation, and that glaciation went from 120,000 to about 18,000 years ago. But the very end of that glaciation was when most glaciers got to their most extensive around the world, including in some parts of Tasmania. So we see that the ice isn't as extensive as it is on the right there. Some places it's just valley glaciers sticking down. You see there's lots of dotted lines because it's hard to exactly connect the dots and know where all they were. But basically, most of the glaciers in Tasmania in the last couple million years have been in the highlands of the western mountain ranges, northern and western margins of the plateau, and a little bit in the southwest. So it's not just that we had ice, the whole environment looked different. So this is Tasmania during glacial conditions, where it's basically almost connected to the mainland here on the left. So you think about this as being kind of a mild glaciation. Now again, the reason this happens is we have lots of water from the marine system locked up in ice sheets around the world. So we actually are basically drawing water out of the bathtub and lowering the bathtub down. So in a mild, cool period, it's almost connected to the mainland. In a more severe cool period, like the end of the last glaciation, it is in fact connected, and that's why the first Tasmanians were able to get down here, as there was a land bridge to get here. It's not just a case, though, that the coastlines change, it's a case that all the different environments change too. So we have, the colder it gets, we have an expansion of alpine areas. So the larger purple area here, we start to have more ice showing up. And just for context or for reference, that red outline is the kind of western wilderness heritage area. So you kind of understand that that heritage area actually contains most of Tasmanian's glacial records. Now the extent of glaciers, evidence of glaciers, there are kind of two types of evidence I work with and that most people looking at glaciers do. There's the landforms, the geomorphology, and then there's the geology, the sediments. So in terms of the landforms, we have some very, typical things you'll find in a geology textbook or geography textbook. There's horns, which are basically peaks that are sculpted on the sides by ice. You have the cirques where the glacier sat, a tarn, a lake and a cirque, and a ret, which is just a sharp ridge sculpted on both sides by the ice. And as you get down to the depositional zone, you have all these different things that we call moraines. And moraines are just kind of the crap that the glacier dumps out. It might be down the side as lateral moraines. It might be at the front as end moraines. And eventually, when the glacier reaches its final extent for that glaciation, it'll usually leave quite a big end moraine that we call a terminal moraine because that indicates the ice terminus. If we zoom in a little bit to that same area, the other way to think about it is to break it up in different types of glacial environments. So we have the proper glacial environments where it was ice deposition. We have, in those environments, till plains, the stuff that a glacier deposits, we call till. That's an example of it there. The scale in that book's just a few centimeters, so that cobble is about 15 centimeters across. Tills basically are just a mix of everything from rock flour right up to clasts. So it can be anything from clay up to house-sized boulders. But the idea is that you have two peaks in your grain size. You've got the fine fraction, the silt, sand, clay, and then you have clasts, pebbles, cobbles, boulders. The types of features we get are these end moraines. If we have that ice deposition in the presence of a lot of water, so basically think of streams on steroids because there's tons of meltwater coming out, then we get what we call glacial fluvial environment, so it's just a glacial environment modified by flowing water. And then we get things like this down here on the right, lots of sand beds, various sizes of gravel, but it's really just, think of the river deposits you see in a river today, but just much, much coarser and much dirtier just because there's so much energy in the system. And then there are glacial lacustrine environments. You kind of see where the pattern is going here. It's a glacial type environment that's having deposition in the presence of standing water. So it's a very kind of quiet environment, and the types of things we get there are, there we go. These kind of horizontally laminated fine sets of couplets. So we have basically thicker clay layers, thicker silt layers that are deposited when there's meltwater in the summer, and it's just dumping out a bunch of fine-grained stuff. And in the winter, when the system quiets down quite a bit, maybe the lake's frozen over in front of the ice, maybe it's a case that there's just very little meltwater in general. It's much quieter deposition, so you get this thin clay layer. So that's kind of a telltale sign that it was a glacial lacustrine environment, is you have these thin, dark clay bands alternating with thick, light silt bands. Just to give an example of some of those. So this is an example of a till, and please come up and take a look at these afterward. But you basically see there's the pebbles in there. It's in this matrix of fine stuff that's kind of holding it all together. I've had to cheat and not bring a geologically recent one because it would have just kind of fallen apart and made a huge mess. So this one's from the Permian glaciations about 300 million years ago. Here's another example of a till. So we've got a clast that was sculpted a little bit by a combination of meltwater and ice, but we have the fine stuff just kind of glommed on there. And that's the glacial lacustrine one. So you can see the fine alternation between the fine dark layers and the thicker light layers. Now, in terms of the morphology, these are some 3D models that you're welcome to come and take a look at too, but things that a colleague and I at MRT have been printing just as another way to try to visualize some of the landscape. So it's nice because you're not just seeing it, but you can feel parts of it too. So for example, these are cirques up here. So we had little glaciers starting in these crevices, filling up. They eventually merged into a valley glacier that came down this outlet here. This is Lake Margaret on the west coast. Eventually, that ice all filled up, and you got an ice cap. When that ice cap was full, it pushed out and it deposited this long end moraine here. So that's a very major feature. That's actually from several glaciations ago. This is the last glacial maximum moraine here. So there's several different generations of moraine shown here. The other thing you can see too, if you tip up an end ever so slightly, there are some little ridges along here. Those are even more muted glacial features. If you run your finger over them, you can feel the bumps. But this is from when the ice cap was much bigger and it flowed out up the top, came down the valley this way. So that's the lateral moraine from an older glaciation still. So we have at least one glaciation there. This is the result, cumulative result of probably 3 glaciations based on the numerical dating, and then the most recent glaciation. So just in that one little area, we have about 5 glaciations in the geomorphic record. Now, I kind of like to think about it in terms of how we've gotten to where we are. So what's the history of people in Tasmania looking at glacial records? The first thing I want to point out is that people were living in Tasmania at least 45,000 years ago. The last glaciers melted 14,000 years ago and peaked about 18,000 years ago. So it's not like this is a new thing. People were living in these environments. In fact, people have lived in Tasmania for longer under glacial conditions than they have since the glaciers have melted. But in terms of a European point of view, when people started kind of looking at these things, it was the late 1800s, early 1900s, and it was really just starting to recognize, you know, there's evidence of glaciation. Usually they'd seen something similar in Britain or elsewhere in Europe, and they're putting the connection together. The first person to really report on any glacial features was Charles Gould, who's the son of naturalist John Gould, who was famous for the book on the mammals of Tasmania, or mammals of Australia, sorry, which the thylacine, of course, featured in. But basically, these were very simple descriptions of the landforms. They didn't go into any details on the sediments. They basically just called everything glacial conglomerate. It was just a big loose term they applied to everything. But we start to see some interesting maps. This is the Lake Margaret area, that same little 3D model I just showed. You see that they're kind of they're a little cartoonish. They're hand-drawn sketches. This one's a bit more detailed from 1895. But you start to see that people, you know, they're fleshing out a bit more detail over time, which is great. And it's really influenced in a lot of ways by what people elsewhere in the world were understanding, particularly in the Northern Hemisphere. So someone would publish in the Northern Hemisphere, oh, I found this, and people would start thinking in Tasmania, oh, we think we've seen something similar, and they'd kind of try to piece it into that Northern Hemisphere story. The 20s and 30s was quite an interesting time. There was a complete change in the suggestion of how Tasmania was glaciated. This was mostly by a fellow named Lewis. Lewis was a lawyer in Hobart, but he was also not just a hobby geologist. He had stints where he was a lecturer at UTAS in geology. But he came up with the suggestion that there was actually 3 stages of glaciation in Tasmania. He said that initially there were these kind of big ice caps that planed everything off. Then later on, there were just the valley and cirque glaciers, and then eventually there were just really, really small cirque glaciers. The evidence he used for this was just the kind of the types of erosion he could see in the landscape. So he was doing, of course, all this on foot. Air photos hadn't been collected yet, so it was really just, you know, little vehicle access. It was on foot and on horseback. But you know, it was these kind of erosional records, like in Cradle Mountain, that he was looking for. Now, in the 1950s and 60s, the conventional wisdom became that, no, we think it wasn't multiple glaciations. We think it was actually just one glaciation like they thought a long, long time ago. And part of that was looking at some depositional features as well. Part of it was revisiting Lewis's site. And they had some real benefits. First of all, they had the first air photos collected in the mid-1940s, so they could actually get the first kind of synoptic view of the Tasmanian landscape. There were new exposures and cores from major infrastructure projects, especially stuff by the Hydroelectric Corporation, so the predecessor of Hydro Tasmania, also new road projects, and the advent of radiocarbon dating, so a technique where you can actually get fairly accurate ages on things, now up to about 50,000 years old. It wasn't quite as old at that time. But the radiocarbon was actually a problem, because this whole story of just one glaciation was based on one radiocarbon sample from the west coast that years later turned out to be not in place. It had rolled down the slope. So it was, we thought it was a step forward. It wasn't probably quite a step forward. But still, this is around the time that Derbyshire and others are producing that glacial map of Tasmania. And again, this is a fantastic piece of work. The story is, of course, a bit different because they were thinking it was all one glaciation, but you know, they're starting to piece in the detail over time. And that's just the the legend that goes with it, just to give you an idea of the types of things they're recognizing. So it's not just a few things. There are all sorts of different ice flow features, erosional features, depositional features. It's a mixture of landforms and sediments. And there's interpretations of where they thought ice limits were and where the drainage divides were, say, within an ice cap. If you have a big mound of ice, it flows out in multiple directions. So they were mapping the ridge on the ice where they thought there was a ridge in the ice surface that you'd have a divergent flow. The 80s and 90s, we're back to the idea of multiple glaciations, and that was driven by several different dating techniques. And a lot of this was done by Eric Calhoun, who was at the University of Tasmania, and many of his students, some of whom are still around in Tasmania. I've spoken to a few of them about their work. But they all did really, really good stuff. So there was the radiocarbon dating they've expanded on for the most recent glaciations. Kevin Kiernan was looking at the weathering rind differences. So basically, if you think about if you have a rock, and it's a rock that's prone to weathering, the longer it sits deposited in the landscape, the more it starts to get weak on the outside. This one here is quite an old clast and an old till. That weathering rind is about 3 centimeters thick. So as I'm carving through that one on the slope, my trowel goes right through the rind and goes ting when it hits the core stone in the middle. So that tells you right there that's an old glacial deposit. And then also paleomagnetism, that's something I actually work with quite a bit. And the idea there is that Earth's magnetic field is a bit of a bar magnet, and it doesn't just do that wobble over time where you have to adjust your compass before you go into the field. It also sporadically does these big reversals. So sometimes the field's the way it is now, so normal. Other times it's 180 degrees off, so reversed. And when certain sediments are deposited, they'll pick up that signature. So if you can measure them appropriately afterward, basically we're looking for, is something normal or reversed? And if it's reversed, it means it has to be older than this last reversal at 780,000 years ago. So really, without more constraint, all we can really say is if something's reversed, then it's older than 780,000 years. If it is normal, then it could be younger than that. It could be this older normal period. It could be this older normal period. So it doesn't help so much in some situations, but it does in others. So kind of the next step beyond that was trying to differentiate actual numerical ages for things a bit more. So a lot of this was based on something called exposure dating or terrestrial cosmogenic nuclide dating. It's basically dating rocks by their sunburns. The longer the rock is exposed out to cosmic rays, the more that rock is changed in terms of its kind of radioactive nuclides, and those are measured, and through a fairly involved process, you end up with numerical ages for certain things. If we go back to that Lake Margaret area, that big moraine there I pointed out in the 3D model, I mentioned there was evidence of it being the result of multiple glaciations. It's from this technique that Tim Burrows, who's now at UNSW, found evidence of not just one glaciation, but at least 2, if not 3 glaciations in that one moraine. So it's a composite feature formed when the ice was reaching the same spot over and over. So from these techniques, we can start to piece together a bit more now. We have multiple glaciations, these black periods, or multiple glacial records in Tasmania, recording at least there's the oldest glaciation. This is one of those marine isotope stages, 10, 8, 6. So right there we have 4 separate glaciations, and the stuff through here is the last glaciation. So we're looking kind of 5 glaciations as a minimum. I like to think about where we can go as the next steps, and one of those is looking at geomorphology, specifically for something called LiDAR. People in this room probably have LiDAR on their smartphone if it's a newer phone, maybe in their car, maybe in some other device. But basically, the way we use it for geomorphology is it's a laser scanner on a plane or a drone, and it's flying over, sending out these pulses, and these pulses are hitting everything not just at the surface, but stuff that's a little bit lower in the landscape as well. And the idea is that you get a point cloud back. This is an example from a mangrove swamp, but you have these, that's the kind of overstory or canopy there. You have stuff in the understory, and then blue as the ground returns. If you're a forestry person or an ecologist, you care about that whole sequence of stuff to understand the biomass and what's going on. If you're a geologist, you process or have all this process to get rid of everything on the top, and all you care about is the blue on the bottom, because we're artificially just stripping all the vegetation off the landscape so we can see a lot better what's going on underneath. LiDAR is not cheap. It can be hard to get. We're lucky in Tasmania that the way it's organized with the state government, it's all publicly available. So we have about 75% state coverage now that you can actually download through the Elvis website, which is a federal website. You can view it for free without downloading anything on ListMap. And probably by the end of this year, we'll be closer to about 82% coverage, which is just fantastic. And this is what the LiDAR looks like. You can see lots going on there. Just for context, that's a kilometer scale up there. I've had to turn the whole thing on its side to north to the right, but this is the upper end of the Mersey Valley. So that's Lake Rowellan. The Rowellan Dam is down here. But you see all sorts of really conspicuous features. There's this sharp line there that goes out this big kind of finger that pokes out that way. That's when ice filled the Mersey Valley. It actually spilled over a low spot just south of Meigs Mountain and spilled into the top of the Arm Valley. So that's the last glacial end moraine. So that's about 18,000 years old. You can follow that feature in the landscape along here, drops down here, comes back off the screen here. But what's interesting to me is these really muted ridges parallel to those, but farther out. That's on top of Meigs Mountain, so higher up. Those are older moraines of similar type when the valley was filled by a much bigger glaciation, much bigger glacier, and it spilled out onto Meigs Mountain and it did the same thing down to the southeast. So just lots of really, really cool features we can find. It's not just glacial stuff. There are, down here, all sorts of landslides, and those landslides specifically are within the glacial material. So that's what I mentioned before about the glacial modification tempers the landscape for natural hazards and other types of issues. So those are probably a direct result of the glacier as it was pulling back. Probably those landslides were happening quite early on in the deglacial history. Now, the other thing I think about too is we've got all these great dating tools, talked about a bunch of them so far. There are always opportunities to kind of combine them in new ways and start kind of getting better age constraint and stuff. So we can use radiocarbon for the youngest. We can use the sunburn, the exposure dating for stuff that's a bit older. The paleomag kind of works as you're getting down into multiple reversals, especially if you have something else you can reference to. The weathering lines and weathering profiles work for some, maybe the last million years. Beyond that, probably it's getting so weathered that it's just falling apart and you can't do so much with it. You can look at biostratigraphy, so different changes in biota over time, so usually fossil pollen and spores. And the whole idea there is we can start kind of putting better constraints on things numerically. So we know that right now, the oldest glaciations we have record of in Tasmania from the recent geologic period are from about 800,000 years ago, maybe a little bit older. The stuff I've worked on in South America, the oldest record we have is about that time in kind of along the Strait of Magellan. Farther north in the Bolivian Andes, it's quite a bit older still. And then in parts of central Patagonia, it's older still. And the question in the back of my mind is, okay, so the stuff that if you went due east across the Pacific and made landfall in the Lakes District of coastal central Chile, where does that fit in? It's the same latitude and probably very similar kind of temperature conditions as Tasmania. Does it match up in this thing where it would be basically the same time as the earliest Tasmanian records? Oops. In the last few minutes, I just want to flick through what I think are some of the interesting glacial stories that I've stumbled across, or other people have stumbled across, particularly in northern Tasmania. This one actually happens to be from the southwest, but this is on Gordon River Road on the way out to Strathgordon. Basically, the Derbyshire's map shows a little bit of glacial evidence here. We don't see anything in the LiDAR, really. But when you look at one of the road cuts, this one right here, you see a couple of neat features. And one of them is this stuff. This isn't glacial, but it's all chewed up. It's all folded, and it's quite young material. So you think, well, how did that get folded? And the answer is that a glacier ran over top of it. So this is the till from the glacier up here, and underneath it's run over the weathered bedrock. It's run over some of the old lake sediments, and it's kind of cut into them, it's chewed them up, it's created little microfaults, it had fluid injections. So the question is, if the stuff below it's non-glacial, does that mean that this is evidence of the first glacier that extended way down into that lowland area? It well might be. A little bit farther north, this is the upper part of the Little Fisher River. So Derbyshire's map has these three end moraines in the valley bottom. If you look at the LiDAR, which we only got just a few months ago, you see not only is there that end moraine, but we can trace that end moraine from the valley bottom here up the sides of the valley as a lateral moraine. And then behind it, we have all these other little moraines. Those are recessional moraines. So basically, the ice sat at the one point farthest out 18,000 years ago, and as it's melting, it's coming back, dropping stuff down. So there's things like this offered opportunities where if we date separate moraines through different techniques, say the sunburn dating, say radiocarbon for the bogs formed behind them, we can actually figure out the rate of loss of ice, so how quickly the ice was disappearing from this valley. This is a spot we went on the field trip yesterday for the GSA gathering, and I think it's a really cool one. So there's a little bit of detail in Derbyshire's map here. There isn't any indication here of a really interesting feature, which is the last glacial end moraine. Whoop. This one right there, if we zoom in. There we go. If we zoom in the LiDAR, it's this ridge right here. So that's about 18,000 years ago. For context, there's a really famous rock shelter just a little bit farther down the valley here. And it had more or less continuous occupation and use from about 40,000 years ago to 800 years ago. So that basically means that the whole time that ice is kind of coming up and down the top part of the fourth valley during the last glaciation, you have people living only 10 kilometers down the valley. Wouldn't have been, I think, a very comfortable place to live, but there were people there at least periodically. You go another 10 kilometers down the valley, though, and you have this much more muted landscape. So this one, as you piece the pieces together, just where the yellow circle is there, you have a nice till, and it's on top of this another glacial lake deposit. And again, there's evidence here of it being all ground up because the till's loading it and cutting down into it. If we go just a little farther down valley to here, we see that same glacial lacustrine unit. It's also eroded a little bit. So there's evidence that there was a lake sitting in the valley bottom here. Now this little nub right there is really interesting. If you go out to it, it's about 8 meters high, 150 meters long, and about, there we go. What this is a piece of bedrock that's been sculpted by ice. So as the ice flows from the south to north over top of that, it's creating this asymmetric profile in the rock. The landform is called ruche moutonné, which in French means sheep rock. Basically, it's shaped like a sheep's butt. But the idea is that as the ice is jamming up against the up valley side here, there's so much force that even though it's frozen and that water is the ice is cold, the pressure forces that ice to melt. So we get super cooled water. So it flows around. It does a good job of smoothing the rock. It gets down to the down slopes or down valley side here, we call the lee side. The pressure is not there anymore, so that super cool water freezes almost right away, and it's kind of just grabbing chunks of rock and plucking it off the downslope side. So that's why we get that very asymmetrical form. So the way I interpret this story, and there's still a bit more work to be done, is that it all ties together. It turns out that these lake sediments, from work done by Mike Pollington in the early 1990s, these are reversely magnetized. So that glacial lacustrine unit has to be older than 780,000 years. The till that cuts down into it, the way it cuts down into it indicates that it's about the same age. And then the fact that this little rounded piece or weathered piece of rock sticks out that's been carved off by the ice, it's all at the same elevation. The same ice would have done all of this. So this is a great little bit of the landscape formed heavily by a valley glacier a little over 750,000 years ago, and we still have a nice bit of record for it. And then just the last example here, this is from the Pieman Valley, close to the Renison Bell Mine. And this is something that a colleague from GHD and I published recently in the Australian Geomechanics Journal. But it's basically talking about how we can use a better understanding of the glacial record to make our engineering projects cheaper and safer and better. So basically the idea here is that we have multiple glaciations recorded. Neither of these are the last glaciation. That's way off the slope or off the screen to the right. But that's a middle Pleistocene glaciation. This is an early Pleistocene glaciation. We know that this is early Pleistocene because the glacial lacustrine stuff is reversely magnetized. But if we kind of look at the sequences and understand not just from the sediments, but also the geomorphology, for example, we see these ridges here. So that ridge is a moraine. This area, before we had LiDAR, was all mapped as glacial lacustrine and glacial fluvial outwash. It's all water-modified stuff. We see a moraine popping through, which means we have to have till underneath because that's a true glacial deposit. And that means without even doing any more work, we can think, oh, there's probably a till there. That means we expect different kind of ground conditions. We have to do our subsequent investigation a different way. We have to think about different types of geohazards that might affect the site. In this case, it's actually probably good news because most of the hazards come from the glacial lacustrine stuff. You don't want to build on that because it can liquefy, it can subside, it can actually have issues where it develops acid soils, whereas the till is a much better foundation. It's competent, it's strong, it's a much better foundation. So the whole point is just by looking at the glacial record and understanding it a bit better, it makes the subsequent work of the detailed engineering a little bit easier. And this just gives you an idea here. We've got the pale pink is the bedrock. The stuff on top is all the glacial stuff. And this, the till unit in orange down here was something that until the geomorphology was looked at and some more detailed drilling was done, wasn't realized was there. And that's just that till. So just a few quick summary points. I'd say most of Tasmanian's most iconic landscapes and probably most important landscapes, in my opinion, were sculpted by glaciers. Now, the ice left all sorts of telltale signs in the landscape in terms of landforms and sediments. And if you know what to look for, they actually stand out pretty easily. There were diverse glacier types, not just little cirques, but valley glaciers, ice caps, and they would have repeatedly formed, expanded, contracted, and eventually disappeared during many of these glaciations in the last 100 million years at least. Over the last 150 years, the stories really come together for us in terms of the modern population understanding what was happening. But there are new technologies and opportunities to combine existing techniques that'll help kind of shed new light. There's still lots of questions to be understood, and there wasn't a lot done on glacial stuff for the last, say, decade or two. Keith Corbett did a little bit of stuff up on the walls of Jerusalem. There were little projects going on, but it happens there's a bunch of us now in government and academia who are kind of ramping up to do some new projects. So there's a whole bunch of collaborators just in stuff that I'm working on. There'll be other people as well that I think maybe in the next decade or two we'll have a much better understanding of what's happened in the Tasmanian glacial record. There's three things I'd love to know. One of them, just in the context of future things to do, I'd love to know when was that first glaciation that really affected the Tasmanian landscapes during the Quaternary. All we can say right now is it was before 780,000 years. People often throw out the number 1 million, somewhere around there. It could be older. I'd like to know was it always a case that the older glaciations were more extensive and they got smaller and smaller over time? Or was it a case that we had some that would periodically be larger? The larger ones end up censoring the record because they bury or scrape away the stuff that was there before. And then finally, I'd be really keen to know how the Tasmanian record fits in specifically with other sites, especially in central Chile. Can you find a glacial deposit here and find a glacial deposit there and say, if they're not the same glaciation, they're at least within a couple? Because right now we can only do very, very broad stroke comparisons. Just 2 bits of free information that you might want to keep an eye out for if you're interested in learning more about the glacial mapping that's been done. That Derbyshire map is it's in the Trove catalog. It's been scanned by the National Library of Australia. Oops, sorry. If you just Google glacial map of Tasmania, Trove, you'll get the right spot. You can download it. It's a georeferenced map, so if you use GIS, you can pop it in there and it'll show up on the right spot. And of course, the other one is the LiDAR stuff from the state government. So you can view this on list map just as the hillshade. If you want to actually download the data and play with it, which is, again, if you're accustomed to working in GIS, dead easy to do. But all this stuff, again, if you just Google Elvis elevation gets you there a little faster. If you just Google Elvis, you'll go not directly there. But yeah, both great resources that we're really lucky to have public access to.
knowledge can really amplify what we have to offer in Tasmania. And I'm wondering, is there any thinking about, as you said, it's more recently that you've been able to get a lot more information, to have the government, who's supporting this, to actually promote that we have these particular places and these particular, so we're not just going mountain climbing or exploring, that we're actually having a tourism kind of adventure, if you like, going out. Is that a possibility in the near future?
Absolutely, and that's actually, it just happens that in the last 2 weeks we've had a lot of those discussions. So I'm already in state government as part of the Geological Sur-vey. I've been talking to colleagues in NRE, including in parks, and also several different academic partners. And what we're trying to shape up right now is a project that does exactly that, ideally focusing on, say, the overland track, where we can really hone in and paint the detailed picture of what happened, and then disseminate that information, including one of the ideas is to have 3D models like this in some of the huts. So you do a segment of the hike, you stop at the end of the day, and there's a little model like this with an information sheet, and you can say, oh, I walked over that. Oh, I didn't know that was a this that records the glacier record. But absolutely, so that's one of my main interests, is going exactly that route. It just, how quickly it happens depends on, you know, what kind of resources and funding we can secure and what kind of partners we can get involved.
Because a simple thing is, at the Cataract Gorge, Peter Manchester often used to comment and say, we need to have some interpretation boards up here because we've got some unique features at that gorge.
Yeah, absolutely.
That are nowhere else, except there's one place in America, I think it's got the same sort of fracture, exposed fracture.
Yeah.
And we need to know that, you know, we need the public to know that it's just part of who we are and what we, celebrate.
Absolutely, and there are a few other kind of initiatives too. Like so Tasmania has a geoconservation database. I'm involved in the reference group for that. We meet once a year to go over nominations that have come in the last year. So we'll sit down, I think it's mid-November, and there's about 12 of us. There's geologists, there's soil scientists, there's geomorphologists, and we'll discuss these features. And you know, something like that, the sheet that I showed, that's what I'm nominating this year. So we'll have a discussion like, how important is this? And in my opinion, super important, because that's the best and most accessible example in Tasmania now. There are some that are now below Lake Roella, so that aren't as helpful. But the idea is that, you know, that information is also all publicly available. If you know where to find the layer for it and list map, you can see the inventory of it. But there's opportunities to spin that into things like information plaques somewhere. Yeah, that's more publicly accessible again.
Question over there. You just wait for the microphone, please.
Yeah, thanks. Very interesting. Just help me to understand how the work you do, glaciation type stuff, fits in with MRT's remit for further exploration and mining within this state and discovery of minerals. I can't clearly tie the two together, but you did mention towards the end something about engineering and a little bit of
So MRT's remit, the name's a bit of a misnomer in a way. Mineral Resources Tasmania is a portion of what Mineral Resources Tasmania does. I'm part of the Geological Survey branch. The Geological Survey branch does bedrock mapping in large part to support future mineral discoveries. We also do geohazards, and that's the kind of main hat I usually wear. So Tasmania is the only state in Australia that has natural hazards as part of the remit of the Geological Survey. So there's a lot of stuff we do beyond just the mineral stuff, but that's certainly part of it. And so the glacial stuff, in part, you know, it's interesting, it's helpful. The bigger picture, how it ties in, is putting together what we call a chronostratigraphic framework for the most recent part of the state's geologic history, last, say, 30, 40 million years. Because right now, a lot of the mapping stuff is focused on the older bedrock. Some of the newer stuff, including alluvial gold deposits and that sort of stuff, if we can understand how the landscape was evolving over about 30 million years, that helps with some of the mineral stuff as well.
Is there very much evidence of glaciation on Ben Lomond?
So Ben Lomond's an interesting one, and it's in this map here. You can see there's a tiny little box up the top right corner in the Derbyshire map. That's Ben Lomond, and there's ice but probably it wasn't glaciers. It was, I think the issue is, so right now we have a precipitation gradient across Tasmania. It's pretty extreme. At Lake Margaret, you get over 4 meters of rainfall a year. On the east coast, you're well under 50 or 500 millimeters. That precipitation gradient would have been the same during glacial times, basically because it's a rain shadow. We have a lot of the weather coming in from off the Southern Ocean to the west. Even though it was cold in Ben Lomond, it was maybe probably too dry. The same on top of Kunani, Mount Wellington. We don't have evidence of glacial effect up there, but we have all the shattered rock and block streams and other kind of features that indicate that we had ground ice that was affecting the slopes, but not truly glaciers because they weren't thick enough accumulations of ice to really get flowing under their own weight very much.
Ladies and gentlemen, please join me in